Hello, this is Mr. Collier, and today we're going to be solving some homogeneous second-order linear recurrence relations. Okay, so that's a bit of a mouthful, but basically if we've got a recurrence relation of this form, okay, where we're using the previous two terms, that makes it second order because we're using the previous two terms, and there's no other function of n, there's no other terms besides the two previous terms. That makes it homogeneous. And it's linear because the terms are added together here. They're not multiplied together or anything like that. Okay, so if you have this form, then you can solve it using this theorem here, which basically states that you can set up the characteristic polynomial and get the solutions x1 and x2, and then you can, if they're not equal to each other, you can use this equation here to find a solution for the nth term in the sequence. Okay, so that's what we're going to do. We're going to show a couple examples here today. Looks kind of complicated here, but it's very easy once you figure out how to do it. Okay, so we're going to be using this in a second. So here's a sequence, okay, a recursive sequence. And we had the first two terms in the sequence, 1 and 4. Now the next term in the sequence we're going to get by doing 5 times the previous term, which is 4, minus 6 times the first term here, which was 1. So we're going to do 5 times 4, which is 20, minus 6 times 1, which is 6, so that's going to be 14 here. Okay, and you can do the same thing for the next term, and you will get 46 for that one, and so on. Okay, so this recursive relation generates this sequence here, and we're going to solve this and find an equation that will give you any term, the nth term. Okay, so that's what we're going to be doing with this theorem here. So let's look at the theorem. Okay, we're going to solve the characteristic polynomial and then use this to find a formula for a sub n. All right, so here we have the formula, and we're going to bring all the terms to one side of the equation. So we're going to have a sub n minus 5a sub n minus 1 plus 6a sub n minus 2 equals 0. Okay, we bring all the terms to one side, and the characteristic polynomial for this is x squared minus 5x plus 6 equals 0. Okay, so that's the characteristic polynomial. That's the polynomial we're talking about in the theorem right here, the characteristic polynomial. And then we're going to solve this to get our x1 and x2. We get x minus 3 times x minus 2 equals 0. So x1 equals 3 and x2 equals 2. It's important to label them x1 and x2 because they correspond to c1 and c2. So it's important to have those labels there. So we've got solutions to the polynomial, and then we're going to use this equation here. Since x1 is not equal to x2, we can use this equation to find a formula for a sub n. So we're just going to copy that over here. I'm going to copy that in green. We've got a sub n equals c1 times x1 to the power of n plus c2 times x sub 2 to the power of n. Okay, and here are our initial conditions. A0 equals 1 and A1 equals 4. We can use that to find the constants C1 and C2. So for n equals 0, we have A naught equals C1 times, now x1 was 3, so that's 3 to the power of 0 plus C2 times 2 to the power of 0, and then of course these numbers are 1, so that's just C1 plus C2, and A sub 0 is equal to 1, so we have C1 plus C2 equals 1. And our other initial condition is that A1 equals 4, so we're going to write A sub 1 equals C1 times 3 to the power of 1 plus C2 times 2 to the power of 1, that equals 4. Okay, so we have 3c1 plus 2c2 equals 4, and we have two equations with c1 and c2, so we can solve that those simultaneous equations and find the values of c1 and c2. Okay, now in this first equation here, we've got c1 plus c2 equals 1. We can say that c1 equals 1 minus c2, and use that and substitute it into the first equation. Okay, so we're going to have 3 times 1 minus c2 plus 2c2 equals 4. 3 minus 3c2 plus 2c2 equals 4, and then we have negative c2 equals 1. And then we're going to have c2 equals negative 1. Okay, so now we got the value of c2. We're going to go on and find the value of c1. Actually, we can use this formula right here. c1 equals 1 minus c2, which is 1 minus negative 1, which equals to 2. Okay, so c1 equals 2, c2 equals negative 1. And now finally, by using our equation again, we get a sub n equals c1, which is 2, times x1. Let me go back and see what that is. So x1 is 3 and x2 is 2. So we get x1 is 3, so that's 3 to the power of n. And c2 is negative 1, so we have negative 1 times 2 to the power of n. And there's our equation for any term in the sequence. We can check it. We know that our sequence goes 1, 4, 14, 46. So let's try it when n equals 3. Okay, so a sub 3 was going to be 2 times 3 to the power of 3 minus 1 times 2 to the power of 3, which equals 2 times 27 minus 8. Now 2 times 27 is 54. 54 minus 8 does give us 46, which is exactly our third term, so it works. Now let's check out the next sequence we have. So in this recurrence relation, our first two terms are negative 5 and 3, and then you get the next term by doing 6 times the previous term. So we're going to do 6 times 3 is 18, and then minus 9 times the term before that. It's going to be 9 times, it's going to be minus 9 times negative 5, which is negative 45. So it's like 18 plus 45, which gives us 63, and the terms get pretty big pretty quickly. So that's the sequence generated by this recurrence relation, and we're going to solve this like we did with the last one and find a formula for a sub n. Okay, so we can rearrange and bring all the terms to one side of the equation. A sub n minus 6a sub n minus 1 plus 9a sub n minus 2 equals 0. The characteristic polynomial equation is x squared minus 6x plus 9 equals 0. And solving that, we get x minus 3 squared equals 0. So we have a double root here. Basically x1 equals 3 and x2 equals 3. Double root. So that's the second case we have here, where we use this formula instead to find our formula for a sub n. So when we use that formula, we have, let me change to a different color, we have a sub n equals c1 x1, or just x in this case. We call them all just x. We don't need subscripts because they're both exactly the same. Okay, so we have, so let me erase that. So the formula is very similar, but with some very important differences. Here's the most important part not to forget is the n here. Okay, we're just going to make a big difference in a second. So our initial conditions are a0 equals -5. So if I put in a0 here, we get c1 times 3 to the power of n, which is 0. So look at that. Plus c2 times 0 times, that should be n up there, times 3 to the power of 0. So this is 0, so this cancels out, and we have, and that equals -5. So we have basically c1 equals -5. So we already have c1, that's pretty easy. And a sub, so it should be a sub 1, should be equal to 3, which is equal to c1 times 3 to the power of 1 plus c2 times 1 times 3 to the power of 1. So we have 3 equals 3c1 plus 3c2. And we already know that c1 equals -5. So we have 3 equals 3 times -5 plus 3 times, oops, sorry, it's 3 times c2. So we get 18 equals 3c2 and c2 equals 6. So we have c1 and c2, so our equation is going to be a sub n equals -5 times x, which is 3 to the power of n plus 6 times, oh, don't forget the n, 6 times n times 3 to the power of n. Okay, so that's your non-recursive formula for a sub n. Let's check that now. Remember our sequence goes -5, 3, and then 63. So we have -5, 3, 63. -5, 3, and 63 for term 0, 1, 2. So let's check a sub 2. That equals -5 times 3 squared plus 6 times 2 times 3 squared. That gives us -5 times 9 plus 12 times 9, which actually equals 7 times 9, which does equal 63. So it appears that our formula works.